It's really hot here, though.
Yeah.
Oh, we're live. We're live.
Well, it's kind of an interesting summer where it's cool in Houston, but it's hot in Chicago, Seattle, and Portland.
Super weird. Yeah, it was 90, like over 90 degrees the entire day on the 4th.
Did y'all have any records like they did in the Northwest, or?
Oh, I'm not sure, but I would assume so. Okay. It's really hot.
Are we live?
Yeah.
Yeah, we're live.
All right, guys, let's go
You
ahead and
hear
get
me?
rolling.
Yeah, we hear you.
Yeah, I hear everybody. Perfect. So for those who are watching this stream later, today we're going to be covering exponents. So we're going to be talking about what exponents are, some rules of exponents, some tricks and things like that. So an exponent, also often referred to as a power, is notation to show that a number is multiplied by itself. And it's written as like a small number to the upper right of your main number. So you can see the notation here is an example. This 2 with a little 3 to the upper right, that means 2 to the third power.
I don't think we can see your screen.
Sorry, what was that?
We can't see your screen.
Oh, y'all can't see my screen. Let me... All right, can y'all see it now?
Yeah.
Okay, I forgot to click share. Thanks for letting me know. So I'll go ahead and take a step back here so I can show y'all what I was saying. Again, we're discussing exponents today, also called powers. And an example of the notation, we have that right here. So you can see this 2 with a little 3 to the upper right of it. That means 2 to the power of 3, or 2 to like an exponent of 3. And that means that you take 2 and you multiply the number by itself 3 times. So the exponent in general is like x would be your number and y would be your power. So as another example, 3 to the 4th would be 3 to the power 4, which means 3 multiplied by itself 4 times. So to work out like the example of what we had earlier, this 2 to the 3, that can be written as 2 times 2 times 2, which is 8. This example over here, it would be equal to 3 times 3 times 3 times 3, which is 81. So that's what exponents are. We're going to work through a couple more examples together real quick. So 2 to the 4. This caret is also exponent notation. So let me mention real quick that 2 with the little 4, the exponent term, is the same thing as saying 2 caret 4. Usually in class, you're probably going to see it written this way with the little number to the upper right. It might be written with a caret sometimes, like that's easier to do on the computer or in a word processor or something like that. But these two different kinds of notation mean the same thing. So anyway, working through the example, 2 to the 4, we know that that means that it's 2 multiplied by itself 4 times. So we would say 2 times 2 times 2 times 2, which is equal to 16. As another example, 3 to the 3rd, that is 3 multiplied by itself 3 times. So that's 3 times 3 times 3, which is 27. This 9 to the 2, or 9 squared, you say a number is squared if it's to the exponent, the power of 2. That's 9 multiplied by itself once. So that's 9 times 9, which is equal to 81. So what if we wanted to work backwards and we wanted to take a big number and write it in terms of smaller numbers to various exponents? That's a process that we call factoring. So factoring is a number, or factoring a number reduces it to the prime numbers that multiply to produce it. If a factored number has more than one of the same number multiplied by itself, it can be rewritten as an exponent. So as a little background, in case you don't know, there are two kinds of numbers. As a little side note here, prime numbers are only divisible by 1 and themselves. So examples of prime numbers would be 2, 3, 5, and 7. The reason being that for each of these four numbers, there's no other whole number that you can evenly divide into it. Like you can't divide 5 by 2, 5 by 3, 5 by 4. You can only divide 5 by 5 to get a whole number. Composite numbers are every number that isn't prime. So they're numbers that are divisible by other numbers. Examples of composite numbers would be 4, which you can divide 4 by itself, or you can divide 4 by 2 to get a whole number. 4 divided by 2 is 2. Another example would be 6. You can divide 6 by 2 to get 3, or you can divide 6 by 3 to get 2. And 8 would be one as well, where you could divide 8 by 2 and 4 to get an even whole number as your answer. So what we're going to do is we're going to factor a number together real quick. We're going to factor 56 as an example. So to evaluate factors, what I like to do is create what's called a factor tree. So we find a number that divides into the number that we're factoring, and we split it up. So that'll be kind of more clear as I work through an example with you. For example, we know that 56 is an even number, so we can divide that by 2. So what we're going to do is we're going to split this off into a little tree. We're going to have 2. And if you had 56 divided by 2, you would end up with what? 28. So just like as a little aside there, 2 times 28 is 56. So now 2 is a prime number, so we can't factor it anymore. But we look over at 28 and we realize that we can still factor that a little bit. So we're going to divide that by 2 again. Bear with me for a second here. Here we go. So we're going to carry down this 2. And we're going to take a 2 over here. And we're going to have 14. Because 28 divided by 2 is 14. So like I showed you on the previous step, if we look at these 3 numbers, 2 over here, times this 2 and this 14, is 56. Now, 2 and 2 are both prime numbers, but 14 still isn't quite a prime number. So we can get away with one more step in our factor tree. So we're going to carry down this 2. We're going to carry down this 2. And we're going to split this again into 2 and 7. And finally, we see again that these 4 numbers we have at the bottom, 2 times 2 times 2 times 7 is equal to 56. So we've completed our factor tree and we've factored down our composite number, 56, into a long series of prime numbers. How we can use exponents here is it's a lot easier to write this out using exponential notation. We know that an exponent is a number multiplied by itself. And at the base of our factor tree, we end up with 2 times 2 times 2 times 7, which is 2 multiplied by itself 3 times 7. So we can rewrite this 2 times 2 times 2 times 7. We can rewrite that as 2 to the third power times 7. It's the same thing, but using exponential notation, it's a little bit easier to represent the number than having to write it out several times, especially as you get to higher exponents. Like if you imagine you had a number that was 2 to the 6th times 3 to the 4th. It's a lot easier to write it this way than to say 2 times 2 times 2, etc., 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 etc. So the exponential notation is a lot more convenient in situations like that. And before I move on to the next slide, I'm going to work through one more example of a factor tree, just to make sure that the concept is relatively clear, because it might make sense to watch it again from beginning to end, now that you know what we're doing. So I'm going to do 150. So we know that 150 is an even number, and 2, so 2 is going to divide into it, and that's going to be a prime number that divides into it. So we're going to split this off. We're going to say 2, and then 150 divided by 2 is 75. That's what we have left over. So we just split up the 150 into a prime term and a composite term. It's the same thing. It still equals 150. Now 2 is prime, but 75, we can divide some stuff into it. We know that numbers that end in 0 or 5 are divisible by 5. So 5 seems like an obvious choice here. So what we're going to do is we're going to pull 5 out of that 75. And 75 divided by 5 is 15. So that's going to leave us with 15 left over. One more time, we're going to be able to pull out 5 again, because the number that we have left over is still a number that ends with 0 or 5. So we're going to pull down this 2, we're going to pull down this 5, we're going to pull out another 5, and that leaves us left over with 3. So what we've done is we've successfully factored down 150 into a series of prime numbers, 2 times 5 times 5 times 3. And if we were to rewrite that in exponential notation, we could just say 2 times 5 squared times 3. And there's our answer. So that's just an example of a place that you might use exponential notation. After you factor down relatively large composite numbers, it's easier to sandwich all the factors together and rewrite the expression, or rewrite the answer using exponents instead of just writing out the prime factors kind of multiplied by each other over and over again. So now we're going to move on to multiplying and dividing exponents. There's some math rules that actually makes this really easy for us. If you're multiplying or dividing similar numbers with different exponents, if you multiply them, you add the values of the exponent together, and whenever you divide them, you subtract the values of the exponents from each other. So note that, like, whenever you're doing that, it has to be the same base number. So for example, if we were to say 2 squared times 2 to the third equals question mark, we see here that we can just go ahead and add the exponent values. So this is equal to 2 to the 2 plus 3, which is actually equal to 2 to the 5th. Similarly, if we were going to do 3 to the 4th times 3 to the 7th, that would end up being 3 to the 4 plus 7, which is 3 to the 11th. Let me scroll down a little bit here. So the opposite holds true too. If you divide, then you subtract the exponents. So if we were to say, what is 5 to the 9th power divided by 5 to the 3rd power? This would be the same thing as 5 to the 9 minus 3, which would be 5 to the 6th. So one thing that I want to note again is that to use these rules, the base number has to be the same. So if you tried to do something like 2 to the 4th times 5 squared, you couldn't end up making it like 2 to the 4 plus 2 or anything like that. You need your base numbers to be the same for your rule to work, for both the multiplication and for the division. So these are, I'll do one more example real quick. Let's do 2 to the 3rd times 2 to the 5th times 3 to the 10th divided by 3 to the 7th times 5 to the 2nd power times 5 to the 7th power. So we have a long series of numbers here with lots of different exponents. And it would be kind of a painstaking process to take each one and solve them and end up with a lot of really huge numbers and then to work through the arithmetic. So first what we're going to do is we're going to simplify. So we know that since these base terms are the same and we're multiplying them against each other, we can just add the exponents. So this would be 2 to the 3 plus 5. Next, we're going to multiply this by, we have 3 to a power divided by 3 to a different power. Since these base terms are both 3, we can just subtract the powers from each other. So we would end up with 3 to the 10 minus 7. And then finally, we're going to multiply this by, we have the same base number raised to different powers. So we can add those powers up. 5 to the 2 plus 7. The resultant here is going to be 2 to the 8 times 3 to the 3rd times 5 to the 9th. So while these are still kind of ugly big numbers if you work them out, at the very least, it's easier to punch something like this into your calculator and solve it out than to work through this long stream of individual terms. So let's see, we have Anastasia and Jaden here on the stream. Are you guys interested in trying some examples of multiplying and dividing exponents? Or would you like me to just keep lecturing and kind of move on?
We try.
All right, you try. I'm going to give you guys a couple problems, and then I'm going to have y'all walk me through how to solve them. So what we want to do is we want to simplify this expression. I'm going to say 2 to the 4th times 5 to the 2nd times 5 to the 3rd. Is there any way that I can simplify this? I open the floor to you guys.
I guess we could simplify like 2 to the fourth, 5 to the second, and 5 to the third.
Mm-hmm. So are there any terms here that we could combine or anything like this? Anything like that to make it a shorter expression?
The 5 to the second, the 5 to the third.
Exactly right.
Yeah.
So what would we do there?
2 to the fourth times 5 to the fifth.
Exactly. She got the answer right, 5 to the fifth. And what she did is she added the exponents for each of the 5 terms. So she took the 5 to the 2, she took that 2, added that to the 3 on the 5 to the 3. The final answer, 2 to the 4th times 5 to the 5th. So she's got it, but I'm going to go ahead and give them one more. I'm going to say, let's do 2 to the 2nd times 2 to the 3rd divided by 2 to the 4th times 2 to the 2. How would we simplify this?
Uh, 2 to the fifth divided by 2 to the sixth.
So close. What we're actually going to do is we have to follow our order of operations left to right. So what this would end up looking like, and I didn't show you guys an example like this, is you would just follow from left to right, adding and subtracting these exponents. So we would say 2 to the 2. Since this is times 2 to the 3, we would add 3. Since this is divided by 2 to the 4, we would subtract 4. And then since we're again multiplying by 2 to the 2nd, we're actually going to add that 2. And this is going to end up giving us 2 to the 3. So it's a little bit confusing because this last term, that 2 to the 2, comes after the divide. But whenever we work this out, we actually just work one step at a time, left to right. So even though it comes after the divide, this last term was a multiplication term. So we just end up adding it in. So one note I want to make real quick about how exponents can make your life easier is whenever we solved this expression by simplifying, we just ended up adding and subtracting the exponents. We got 2 to the 3rd, which just leaves us with 8. If we were to work these out individually, what we would have done is we would have said 2 squared is 4, times 2 times 2 times 2 is 8, divided by 2 times itself 4 times is 16, times 2 squared, which is 4. And we would have had to have worked it out and said 4 times 8 is 32, divided by 16 times 4. 32 divided by 16 is 2. 2 times 4 to get our same answer, 8. So it's not so hard whenever you're dealing with 2's, but if you were to do this same problem and you say 7, if you had 7 squared times 7 to the 3rd power divided by 7 to the 4th times 7 squared, it's a lot easier to solve that out and solve 7 to the 3rd power than to work out all of these big numbers individually and add them and subtract them into each other. So everything that we've covered so far is positive whole number exponents. And now what we're going to move into discussing are square roots. And like what the square root is, or whenever you have like a fractional exponent, which I'll explain more in just a second what that is is it's actually the opposite operation of taking a number to the exponent. So we ask ourselves the opposite question. Like an exponent, you would have a base number to the second power. We would rewrite that, or we would say that's the number times itself, and that's your answer. What the square root is asking you, if you take the square root of a number, is you say, hey, I have this composite number right here. What number times itself is equal to this number? So it's kind of just the opposite operation, and that's going to make more sense once I show y'all in just a second. Give me a moment to erase what I had on this slide already so we can work through it together. All right. So square roots. What does that notation look like? Similarly to exponents, how we could write it in two ways. As an example, you might have 2 squared being equal to that 2 caret 2 notation I showed y'all earlier. A square root is written in two different ways. If we were to take the square root of 2, you could either take 2 to the 1/2, which, if you notice, that's just the opposite, or the reciprocal of this first term up here, instead of saying 2 to the 2, which is the same thing as saying 2 to the 2 over 1, because 2 is just 2 divided by 1 as well. We could flip that, and we would say 2.5 is our square root. Or we use this symbol. It looks kind of like a division symbol with an extra line in front of it. This square root symbol, square root 2. So that's the same thing as saying 2 to the 1/2. And what that square root does is it is telling us to work backwards and find out what number multiplied by itself is equal to that number. As a couple examples, it's kind of hard to evaluate 2, so we're not going to evaluate that one. We're going to say, what is the square root of 16? So to find the square root of 16, what you want to do is you actually work backwards and you say what number times itself is equal to 16. So if you think kind of like in your head, 2 times 2 is 4. That's not big enough. 3 times 3 is 9. Still not quite big enough. 4 times 4, that's 16. That's our number. So whenever we take the square root and we're asking ourselves what number times itself is equal to 16, we say, hey, we got it. Our answer is 4. Similarly, the square root of 9, asking ourselves what number times itself is equal to 9. We figured that out earlier whenever we were thinking about it. 3 times 3 is 9. We would end up saying, hey, our answer is 3. And finally, if we were to take 4 to the 1/2 power, remember, that's the same thing as the square root. It's just a slightly different notation. We would say what number times itself is 4. We could work that back and say that would be 2. So that's what a square root is. Kind of like with exponents, you're not limited to just raising it to like the second power. You can also take what's called the cubed root, or the fourth root, or the fifth root of a number. So as an example, like if 2 to the third power, you're saying it's 2 times itself 3 times, or 8. The opposite of that would be the cubed root. You would write it with similar notation. as the squared, except you'd write a little 3 on your symbol. Or instead of 1 over 2 as your power, you could have it to the power of 1 over 3. And what we're asking ourselves whenever we're evaluating the cubed root is we say we have some number. What number multiplied by itself 3 times is equal to that number? So as we saw above here, 2 times 2 times 2. So 2 multiplied by itself 3 times is 8. So the cubed root of 8 would be 2. As another example, let's ask, what's the cubed root of a larger number, let's say 125? So what number times itself 3 times would be 125? We can work our way up. We can say, well, what is 3 times itself 3 times? 3 times 3 times 3 is 27. That's not big enough. So let's go up 1. 4 times 4 times 4. That's 64. Still not quite big enough. So let's do 5 times 5 times 5. That gives us our answer of 125. So that means whenever we evaluate what is the cubed root of 125, or what is 125 to the 1/3 power, that is equal to 5. The fourth root would be the same thing. You would write that as a little 4 on your square symbol times some number, or some number to the 1 over 4. I should note real quick that whenever I write this x, what I mean by that is x is some number. So x can be any number. It can be 0, it can be 1, it can be